Hello and good afternoon, everyone. Today, inshallah, we will continue on our topics, on our topic of today, which is the coordinates and the vector spaces. Just a second, I'm searching for my electric pen. Okay. Yeah, here we go. As I was telling you, today, inshallah, we will continue the topic of vector spaces. We will go through coordinates today. I hope this lecture will be nice and accessible for you. Of course, all our course notes and everything, references and the videos and supporting materials, you will find them all in Moodle. Also, I will send you the PDF for this lecture as soon as we finish it, inshallah. Today I will talk between the bases, but mainly we will go through coordinates and what we mean about coordinates as you will see. The topic is really very simple. Once more, I want you to remember what is the basis. A basis, let V be a vector space, and the beta is a subset from V. We say that B forms a basis for V if we have simultaneously two conditions, they have to be satisfied. First of them is we have linearly independent set of vectors which are which belongs to the basis B. And second, those bunch of vectors or this set of vectors are enough to generate any other vector which belongs to the V set. Usually, when they are linearly independent, they will be able to generate all the vectors that belongs to B. Note, if a set forms a basis for a vector space, the order in which we consider the vectors is very, very important because also and relevant because the coefficients that you will depend on in order to get another vector, their order is also very important. Okay, so according to our remarks, I want you to know that we also went through dimension. The dimension of Rn is simply the number of vectors in the basic generating series, so it's n. And also for the dimension for the set of matrices m by n is equal to m times n. Okay, that's for the dimension of the m by n matrices. The standard bases usually are the set of vectors which have just only one at the pivot of each row and the remaining elements are equal to 0. So in specific for any E of I, it's going to be zeros, as I told you, except the pivot of this vector, which is going to be 1. Those symbols will make, or those two examples will make it really very clear for you. So if I'm talking about the standard basis or the canonical basis for R2, as we already know from our previous session, it's 1, 0, 0, and 1. And those two vectors with respect to R2, they are number 1, linearly independent set. Number 2, they can generate any other vector belongs to R2. For R3, same way like we will have 3 vectors. It's like 1, 0, 0, 0, 1, 0, 0, 0, and 1. And those 3 vectors also represent a basis for R3. And they satisfy both conditions. First of all, they are linearly independent. Number 2, they can generate easily any vector belongs to R3. Usually, we call them the standard basis of Rn, or we can call them the canonical basis of Rn. Both two expressions can be used in parallel and they are relative to the standard basis, as I told you. Okay, now this theorem is really very important. Let's V be a vector space and the beta one of its bases. And if V belongs to the vector space V, then there is just only one linear combination of the vectors in beta which is equal to V. This confirmed that for each vector belongs to the vector space V, there is just only a linear combination, a specific linear combination, which means a specific coefficients that you can use with these vectors and you will be able to get your vector. Okay, what are the coordinates? The coordinates simply and directly are those coefficients, C1, C2, up to Cn. Those what we are calling the coordinates of this vector space with respect to the basis of beta. So once more, let V be a vector space. Beta is the basis for this vector space as an ordered set, a basis for V. And if we want to get U, a vector of V, all we have to do is to find the coefficients C1, V1, C2, V2, up to Cn, Vn, according to this basis. We call the coordinates of U with respect to basis beta, and this is really very important. We call this statement the coordinates. So the coordinates simply are C1, C2, C3 by their order. And usually we symbolize it by this is the vector U and this is the coordinates but with respect to basis beta. So those numbers are C1, C2, Cn. Once you take them and use them with the basis, you will be able to get the vector U. This problem or this issue is really very important, and as you saw, it's easily evaluated. We already know most of this from the linear combinations, so there is nothing new. Let's look to this question. He is giving you, write the vectors, write the vector 1 to 3, which belongs to the vector space and which of R3, and which have two bases. This is the standard or canonical basis, and that's another basis. Okay, simply, if I want to write the vector 1, 2, 3, if I want to write the vector 1, 2, 3 as a linear combination of the canonical bases, this is very, very simple. It's gonna be 1 times 1, 0, and 0, plus 2 times 0, 1, and 0, and this is plus 3 times 0, 0, and 1. Now, I can write that for vector V with the canonical basis zeta, the coefficients are 1, 2, and 3, which are the same image of the vector. Okay, once more, if I want to get the coordinates, okay, of vector V, but not with respect to the basis, the standard basis, with respect to basis number beta. This is really very simple. It's exactly finding the coefficients that I can use with this basis in order to get our vector. So simply, all I have to do is write 1, 2, and 3, and this is equal to C1 times 1 double 0 plus C2 times 1, 1, and 0 plus C3 times the triple 1. And simply, I can solve this system of equations and get the coefficient C1, C2, C3. I can do it in many ways, but the simplest and the one that I usually like to use is forming directly the augmented matrix, which is going to be 1, 0, and 0. Then I will have 1, 1, and 0. Then I will have 1, 1, and 1. And this is the result or the vector that I'm aiming to have. It's really very simple. All I have to do is to complete the solution or to finish up this equation, which is simple. If I multiply the second row by -1 and add it on the first row, so it's gonna be simply, especially the first column is already correct, so it's gonna be 1, 0, and 0. For the second row, it's gonna be 1, 1. Also, this is 2, multiplying by -1 and adding on the first row. So -1 plus 1 is gonna be 0. -1 plus 1 is gonna be 0. -2 plus 1 is gonna be -1. Same way like the last row is already exists. I will use it, okay, already set. I will use it in order to force or to reach the reduced echelon form. And this is really very simple. All I have to do is to multiply the third row by -1 and add it on the second row. So simply I would have 0, 0, and 1. This is going to be 3. Multiplying by -1 and the adding, so it's going to be a 0, 1, and 0. -3 plus 2 is going to be -1. That's for -1, 0, 0, and 1. Now I have the coefficients. So the coefficients simply will be, this is -1, that's -1, and this guy here is 3. Now I can write, this is the vector v with respect to the basis beta. The coordinates will be -1, -1, and 3. And this is how we can write, how we can find and write what's called coordinates, which is really major. So this is the way to find a coordinates for the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. And this is how to, for the standard basis. And the advantage in the standard basis is exactly the vector will be with the coordinates. Okay? But if we want to find the coordinates but with respect to another basis, this is mainly or generally the main steps that we will do in order to gain or to have the value of these constants, and so knowing the coordinates that it can generate vector v out of this basis. This is really very important. Okay, once more, according to all of this, I will redo it again, but with our slides as we usually do. So, it's really very simple. Now I will go through it step by step. First thing, okay, now we can get vector v, which is 1, 2, 3, from the first basis. This is the first basis, which contains the 3 vectors. So v is going to be 1 times 1, 0, 0, 2 times 0, 1, 0, 3 times 0, 0, 1. That's the linear combination of the vectors in zeta, as I told you. And we can get vector v 1, 2, 3 from the second basis, which is beta. And also in a similar manner, as we solve it together, it's going to be -1, -1, and 3, which is a linear, which is a unique linear combination between these set of vectors in order to develop the vector v, which is 1, 2, 3. So remark, the coefficients of the linear combination and their arrangement with respect to the set of vectors of the beta basis is really very important. This is the formulation of the standard basis, which is 1, 2, 3 times the 3 vectors of the standard or the canonical basis. And those are the numbers which are the coordinates that we can use for the basis based on B. Both of them can be really easily written. So coefficients used in the linear combination of V with respect to zeta is 1, 2, 3. For the vector with respect to beta, it's -1, -1, and 3. And so we call them the coordinates. And in specifically for B, it's going to be V, the coordinates of V with respect to B is -1, -1, and 3, as you can see. Remark that the concepts that exist here in this slide and in this manner, it's a connection between what's happening in matrices, what's happening in an application of multiplication and the gathering the all the topics all together. The definition of a basis, you should know exactly what's the definition of a basis, how to get the coefficients, and of course going through the linear combination. Okay, another problem, consider beta 1, 2, 3, 4, 5, and 6, and I want to generate another vector. I'm sorry, the sign of the projector just hide it, but it will appear now. And what are the coordinates of vector 12, 15, and 19? In a similar manner, here I'm asking about the coefficients. So once more, it's really very simple. This is the first vector. I will multiply by C1, K1, or alpha 1. This is the second vector. That's the third vector. Multiply in the coefficients. He needs me to find the coordinates, so all I have to do is to find C1, C2, and C3. That will generate the vector 12, 15, 19 out of the set which is U1, U1, U2, U3. Once more, I can do it either by forming the system, which is AX equal to B, where A in the matrix of the vectors, taking the vector as columns, X stand for the coefficients C1, C2, C3, and equal to B, which is 12, 15, and 19. So I can solve this system either by writing A X equal to B, where A is the vector that I can form from these vectors as units. So simply, that's the system of equations that we are talking about. That's the system that I was telling you. That's the A matrix. This is the A matrix. That's the X matrix, and that's the B matrix. I can solve it in plenty of ways. I can get the inverse of this matrix and multiply it by 12, 15, 19. This way I can get C1, C2, C3. Or to develop, as the previous problem, an augmented matrix with this is the coefficient and that's the result matrix. And in this how, if we, either way, if getting the inverse multiplied by 12, 15, 19, or solving this augmented matrix, once more, the augmented system could be easily like this. This is the first vector, 1, 2, and 3. The second vector, which is 4, 5, and 6. And the third vector, which is 7, 8, and 10. And I will solve it with respect to the results 12, 15, and 19. Solving this system and reaching to the reduced echelon 4. If you work it like this, you will end up having the values of the coefficients, which are 1, 1, and 1. Exactly like getting the inverse first for this matrix, then multiply by 12, 15, and 19. Then you will have C1, C2, C3. And now I can write that the basis or the coordinates of vector V, but with respect to the basis beta, are 1, 1, and 1. Which means simply, for the last time, I can generate this vector by simply considering C1 is equal to 1, C2 is equal to 1, C3 is equal to 1, and we'll be able to generate this basis. So as you can see, the topic is really very simple and it is accessible. You can get it really very easily. For the second problem, or for this problem, consider also the basis beta with 3 vectors. He's asking you what are the coordinates of U with respect to the standard basis, remark the standard basis of R3, knowing that the coordinates of U with respect to beta are 1, 2, 1. This problem is really very good. He is giving you 2 things together. First of all, he is giving you the basis and give you the coefficients which will build the vector U. Once you have the vector U, he wants you to find the coordinates of U, but with respect to the standard basis or the canonical basis. And once more, this problem is really very simple. Okay, so simply I can do what? I can do writing that the U vector will equal to the coordinates, which are 1 times the first vector 1, 2, 3 plus the 2 second coordinate times the second vector, which is 4, 5, and 6, and then the third one, which is 1 times the last vector, which is 7, just less than a second please, which is simply just less than a second, 7, 8, and 10. Okay, 7, 8, and 10. And this way I can get the value of U. There is another way, okay, to get the vector U. I can say that vector U is equal to, I will multiply the matrix, which columns are the vectors, which are 1, 3, 4, 5, and 6, 7, 8, and 10 times the coordinates, because I have them, C1, C2, C3, which are 1, 2, and 3. And the result will be vector U. This is going to be the coordinates, the components of vector U. So just simply multiplying the row by the column, which is going to be 1 plus an 8 plus 7 times 3, I will be able to get those guys, or these are the values of U. Which can be easily, if let's do it step by step. So it's a 1 times 1, which is going to be 1, 4 times 2, which is going to be 8, the sum is 9, and 7 times 3, which is going to be 21. So adding them together will give you a 20, I believe. Please review the numbers and the multiplication after me. 2 times 1, it's 2. 5 times 2, it's 10. So a total of 10, 12. 8 times 3, which is 24, plus 12, I believe this guy is going to be 36. And once more multiplying the last row by 1, 2, 3. So it's a 3 plus 12, which is going to be 15, plus 30. So this guy is going to be 45. It's exactly like this. 1 for the first component, 2 times 4, which is 8. 8 plus 1 is going to be 9 plus 7, so it's going to come up to 16. Okay, so I'm sorry, this guy here is just only 1, and okay, it will correct these numbers. I'm sorry, I just wrote the third coefficient, the third coordinate 3. Once more, as I told you, if we multiply the row by the column, so it's going to be 1 plus an 8 plus an 7, so it's going to come up to 16. 2 times 1, which is 2, 5 times 2, which is 10, so it's going to be 12 plus 8, I think this is going to be 20. 3 times 1, which is 3, that's 12, it's going to be 15, so it's going to come up to 25. Once more, if we add those numbers, this is going to be 3, that's going to be 12, so it's a 15, plus a 10, so it's going to be 25. So either way, either writing the coefficients times the vectors, it will develop U, or taking the vectors as a matrix A with columns are the vectors and multiplied by the coefficients, and you will find your vector. Once I have U vector, so now U as a vector, which is 16, 20, and 25, I can write U with respect to the standard basis, and which is going to be X 16, 20, 25, because simply those numbers are 16 times 1, double 0, plus 20 times 0, 1 and 0, plus 25, which is 0, 0, and 1, which are the coordinates, but with respect to the standard basis, which are 1, double 0, and 0, 1, and 0, and the last one is 0, 0, and 1, as you can see. So I can get the vector U either by the main linear combination equation, or doing the matrices issue, multiplying the A matrix by the column of the coordinates, and you will have your vector. You have your vector, you can write it simply as coordinates, because those are the coordinates and the vector at the same time. If we multiply the coordinates by the canonical basis or the standard basis, which is 1, double 0, 0, 1, 0, 0, 0, 1, you will be able to get your vector. So this is really very important, how it is all connected together. Let's do it once more with our slides. Okay, so as I told you, once more, in this problem, it is given the coordinates which can be used with the basis. These are the coordinates, this is the basis, to get a new vector, which is V. And this is really very simple. All I have to do is to multiply 1, 2, and 1 times the vectors that I have. This is the general form of the vector, which with respect to standard basis can be written like this. Okay, so that's the coordinates. Also, I can get it exactly by getting the vector in a matrix form, multiplied by the coefficients, and this is going to be our vector, which once more can be written in with respect to the standard basis. Also, in this problem, we have 1, 2, 3, 4, 5, and 6, and what are the coordinates of V, this vector, with respect to basis beta. So once more, I need to find the coefficients C1, C2, C3, that using them with those vectors will give you that, with this basis will develop that vector, which is once more on a matrix form. I will write it also. I want to stress on this fact that this is the A matrix, and now I'm looking for the coordinates. So C1, C2, C3, that's the column matrix that I want to have, and the vectors is already here, which is 12, 15, and 19. This vector, I can get it from the basis, so it's 1, 2, 3 for the first vector, 4, 5, and 6 and for the second vector, and that's the third vector. Solving this system either by getting the inverse of this matrix multiplied by 12, 15, 19, or making an augmented matrix and solving for C1, C2, C3, both of them are okay. Once I have this, now I can get the vector V with respect to basis, and those are the coordinates, the value of C1, C2, C3. It's exactly the same. I will do it with you with the slides, step by step. Okay, so as I told you, once more, in this problem, we will get the values of the coordinates with respect to beta. So it's really very simple. This is C1 times 1 to 3, C2 times 4, 5, and 6, C3 times 7, 8, and 10, and it's equal to 12, 15, and 19. That's the system of equations. I'm looking for the coefficients, so I can get the inverse multiplied, or writing an augmented matrix and solving for C1, C2, C3. Once more, those are the values, which is the triple ones, so the basis is known. Those problems are really very important, and they are direct. If you remark, once more, this is, we are talking about the basis and the coordinates, and we will go through the null row and the column spaces down the road. Okay, consider the problem 1, 2, 3, 4, 3, 0, and 7, basis of R3. Okay, the summary of the previous two problems is already here. The last two problems, one of them I've gave you the coordinates and I've asked you about the vector. The other problem, I was asking you about the coefficients or the coordinates that will develop certain vector. So in this problem, what are the coordinates of U1 to 1 with respect to the canonical basis? In such a case, I'm giving you the coordinates. So all I have to do is to multiply the coordinates by the matrix, by the given matrix, and we'll be able to get the value of this vector, which can be represented as a coordinates of the standard basis. So either by multiplying 1 times the first vector, 2 times the second vector, 1 times the third vector, which will develop your vector, or getting the vector from all three columns, that's it, and multiplied by 1, 2, 1, which are the coordinates given, I will have the vector. Either way, the standard basis is 16, 20, and 25. Remark, this is the matrix that we develop from the basis. Or, if it is required, like this problem, what are the coordinates of V, of this vector, 12, 15, 19? In such a case, or in this problem, I'm not giving you the coordinates, but I want you to get the coordinates. So, in this part, or in this problem, you have your coordinates, and I'm getting the vector. It is the contrary. I'm giving you the vector, and I'm asking you about the coordinates. So simply, I will form C1, 1, 2, 3, C2, 4, 5, 6, C3, 7, 8, and 9, is equal to 12, 15, and 19. So we can simply perform the system of equations. Solving this system for C1, C2, C3, Either by getting the inverse and the multiply, or by solving this augmented matrix, you will be able to get the triple Y. This is measured to understand the difference between this problem and that problem. This problem, you have your basis, you have the coordinates, then you will be able to get your vector. In this problem, you have your basis, you have the vector, and I'm searching for the coordinates. So there is a huge difference between these two problems. In general, let B a basis of Rn. The change of basis matrix, is simply the matrix which columns are the vectors of this basis that we were using in the previous two problems. So B in the invertible matrix B, which columns are the vectors of the basis, as I told you, respecting the stipulated order that exists in your basis. So it's really very simple. Now, when we multiply B with the column matrix whose entries are the coordinates, I will be able to get the vector. If I want to get the coordinates, I will multiply the vector by the inverse of this matrix. This is the inverse. So that's stand for problem number 1 that we solved it together, and that stand for problem number 2 that also we solved it together. So once more, if I want to get, those are the coordinates, this is the basis, are given. So all I have to do in order to get a vector, it's to evaluate a vector, all I have to do is write once more, okay, once more I can write or get the vector directly simply by multiplying the matrix with columns 1, 2, 1, 0, 1 and 0, 2, 2, 0, it's the matrix of the transformation of basis, times the coordinates which are -1, 5 and 2, and the result simply will be 3, 7 and the -1. If you multiply the first row by the first column, so it's going to be -1, that's 0 and that's 4, the sum is 3 and so on, you will get your result. So it's really very important problem. Okay, once more, as I told you, this is the coordinates, mainly the matrix and the coordinates. If you multiply them together, you will get your V matrix exactly as I told you. This is the B, this is -1, 5 and 2, which are the coordinates given, and you will be able to get your system or your vector. Once more, this problem, it is the contrary. You have the basis, and now you have the vectors. I need to get the coefficients. So all I have to do is to multiply in the inverse of this matrix or to solve the system. So that's the system of equations. I will get the inverse multiplied by -1, 0 and 1, and then I will have the coordinates which are 1, 0 and the -1. And on a matrix form, when we multiply the inverse beta, okay, in the vector, I will get my coordinates. This is how to get from the vector the coordinates or to get the vector from the coordinates. This is really very important, okay? As I told you, it's really very simple. Direct substitution, but you have to understand it very well because it is confusing. You have to know the vector, the coordinates, and how to use them optimally. There is some exercises here, okay? Let's see one of these problems. It's really very simple. The first two, at least, I will do them today, and I will leave the rest for the next lecture, inshallah. You will, for each case, find x, given its coordinate vectors, with respect to the basis of beta. So that's the basis, and those are the coordinates. It's really very simple to get the vector, simply by multiplying the first column by 5 and the second column by, multiplying the first vector by 5 and the second vector by 3, or simply form the matrix, which is simply 3, -5, -4 and 6, and then multiply this matrix by the coordinates, which are simply 5 and 3, and then you will be able to get your intended vector. Similar manner for question number B. So if I want to evaluate it simply, all I have to do, this is the main basis. I can do either multiplying by 5 times the first vector, 3 times the second vector. So x is the vector which is 3 and -7, that's the result. And for the triple, I can do it also for number B, either by doing exactly the same or by forming a matrix, okay, as we talked previously, writing the vector by the first vector as the first column, the second vector, which is 5, 2, and the -2 as the second column, and the third one, which is 4, -7, and 0, and then multiplying it by the coordinates, which are simply 3, 1, 3, 0, and the -1, and you will be able to get your x, which is the new vector. So if I want to try them, 1 times 3 is going to be 3, 5 times 0 is 0, 4 minus 1 is going to be -4, so the first component is -1, as you can see. The second component is going to be -12, this is going to be 0 plus 7, which you will end up having -5. Multiplying 3 by 3, it's 9, -2, 0, and 0, so the last one is 9, it's exactly the same as you can see. So it's really a very simple problem, as you can see, either using the coordinates with the basis or writing the matrix and the multiplying by the coordinates as you see. Also, for the second problem, and this is problem number 1, those are the results exactly as we have, 3 minus 7, and the -1, -5, and the -9. Here's exactly the same. Here's in each of the following, find the coordinates. I want you to find them. So in the previous one, you had the coordinates, you had the vector. Now I'm giving you the continuity. I'm giving you the vector and the coordinates, and the vector and the basis, and I'm asking you about the coordinates. So simply, if I want to solve for the first problem, I can form simply 1, -2, and 0, and then 5, -6, and 1, and then triple ones. This is triple ones.